5 o'clock. I could tell when it was one more minute.
Tried to close the doors to the room and failed. So
Well, I don't have uh, any advice on that. Well, we are officially at start time, and I think nobody will feel slighted if they miss the first chair slide, so let's get started. Uh, Hi, my name is Ben Schwartz. Together with Sam Weiler, we are the chairs of Privacy Preserving Measurement, and this is the very first meeting of this brand new IETF working group. Thank you to Joe Salloway for being our surrogate chair in Vienna. If you have any questions in the room, please take them to Joe. Sam and I are both on in East Coast time in the United States. So uh, if we say anything that seems a little silly, it's because it's still pretty early in the morning here. Okay, how's it going, Joe? Are we ready to go in
I
in the
think I'm
room?
just trying to get, right now the doors to the room are open and there's kind of I think a lot of ambient noise coming in, so I'm trying to get them closed. So I think we're ready to go. I mean,
Okay. Well, as long as it's not too distracting in the room, maybe we can keep moving. Uh, As always, please note well that you have certain obligations and expectations by participating in an IETF session. It's always relaxing to be the last session at IETF, since most people have had a chance to really look at this quite a few times this week. But just in case you haven't, this is legally binding. So please understand what's going on here and abide by these rules when participating at the IETF. Uh, this is a hybrid meeting. If you're in the room, you probably know that you need to check in with your mobile device in order to be counted as attending this session. Please do that. And there are some resources that we've been encouraged to share with everybody. And this is our agenda. We're starting off here with a chance for anybody to ask questions about the agenda. Then we'll have an introduction to PPM from Eric Riscorla. That seems like a good way to start off the very first session of a new working group. Then we'll have some discussion of a draft that's mentioned in the working group charter and some changes that have happened to that draft since the working group forming above, and also a new draft that takes a different approach to some of the problems we're discussing here. And hopefully we'll have enough time after that to really get through everybody's questions and maybe even end ahead of schedule. So that's all we've got for this meeting. If anybody wants to raise questions about this agenda, please speak now. Otherwise, we'll hand it over to Eric Riscorla.
I am talking next, obviously, but I did have a question with the agenda, which is we probably need to talk about adoption of the draft, because that is a charter item in two ways. So so just like that should go at the end of this, at the end of in the beginning of this region changes, etc.
Okay, I think that we will note that that we will definitely raise the question of draft adoption after the presentations in this during this session. Thanks. And now it's yours. How do you want to handle slides?
I think if I just press this button, which I can never find, then we should be good. Or now you have to press a button.
Yep. Oh, I see. I need to stop sharing before you can start sharing.
Or I can just talk to your slides, which would be entertaining. All right, overview, right. So for those of you who attended the BOF, this is actually a nearly identical presentation. So my apologies not for giving it, but for the fact that you had to wake up 20 minutes earlier than you otherwise would have. So if you've already seen this, you can feel free to go get a coffee or something, because it really is just a subset. So the sort of order of this presentation is, first I'm going to talk a little about measurement scenarios, namely the things we're actually trying to accomplish. Then I'm going to talk a little bit about various methods of anonymous measurement, trying to set in context the work we're doing here. Apologies to the STAR people, I didn't actually cover STAR in this, but they're going to, so that'll be fine. And then I'm going to talk some about MPC, the specific technologies, which are the ones that are like largely in the scope of this working group. Again, this is mostly stuff in draft GPEW. I'm expecting Chris to cover a lot of the detail, but this is just to give you sort of some situation. And I think we'll stop. So there are a number of situations where it's desirable to learn information about people. This is not only true on the internet, but it's true generally. Various forms of public research. The census is a good example. Wish to learn information which is highly sensitive, like demographics, income, medical issues, those kinds of things. Having a sense, for instance, of how many people have had or having COVID is obviously very important for COVID response. As an example. Then there are commercial reasons, for product development. If you make a product, you'd like to know which features people use and don't use in your product, so you can make them better or take them out. You'd like to understand where your product is failing to work, and this is obviously very important for consumer products that that people use and they go wrong, and so. If your product doesn't work on a website, it's a pain to have customers have to report it to you. So you like to know it didn't work, and like to measure where it didn't work. So which ones are most important. This is a big issue for Firefox, by the way. And then there's various kinds of behavioral measurements that are how people are using your product. For instance, we discovered websites which didn't previously existed. So you could people are now going to the website a lot. Maybe it should be, I don't know, in the search index. And which information people are most interested in. Again, maybe this should be something which you'd like to have a search index or like to tell them about proactively. So there's measurement is all over the place. So this information is obviously super useful, but the problem is it's also in many cases very sensitive. People. So take my example from earlier. Having it known that someone had COVID or had some other medical issue, that's information they may not wish to be known. Income, sexual orientation, all these things are gender identity are things people, an aggregate, people would like to know, but individually people necessarily do not want to disclose. And it turns out that that even much less sensitive data can, or apparently less sensitive data can actually be very, very revealing. And especially when you take a lot of less sensitive data. I got this in scare quotes for a reason. It's not emphasis. It's reminding you that less is a matter of judgment. When you put a lot less sensitive data together, you learn a lot about people. And so there's this famous incident where Target sort of looked at somebody's shopping history and figured out that this girl was pregnant. And I've heard other reports from people the same thing, that they'll be anticipating some life change, and they'll suddenly start getting advertising that that anticipates that life change. And this kind of concept is the foundation behind modern web advertising, that you sort of take a bunch of small information and glue it together and use it for targeting. So it's definitely the case that collecting a lot of information, even if it's nominally not sensitive, can be a real problem. So there's tension between information gathering and the power of information gathering you like to have, and the privacy problems that creates. The good news, however, is the tension is created by technology. It's not inherent. Because mostly what you want to gather, I want to caveat that that's not always the case. So for web advertising, for tracking, it's super complicated. But for measurement, you typically want to measure aggregates. So you want to measure what is the distribution of people's income. I don't care anybody's individual income, I like the distribution of income or distribution of household expenses. You want to know what fraction of people have had COVID. You don't want to know whether anybody individually had COVID in general. I mean, obviously there are cases, like the people in Vienna, perhaps, where you might want to know if someone individually has COVID. But from my comfortable posture in my room here, I don't care. I don't need to know, which individuals in Vienna have COVID. Is there there's more complicated aggregates. So you might want to measure the relationship between income and height, which, by the way, there is one. Taller people tend to have higher incomes. What are the most popular websites? Again, I don't need to know websites, individually someone went to. All I need to know is, which websites are most popular. It's often necessary, however, not just to have gross aggregates like that, but to be able to slice the data in multiple ways. So you say, well, I want to know what's the distribution of people's income in California, or I want to take two arbitrary variables and compare them. So I gave this, income and height distribution example, but you might want to say, well, COVID rates sliced by age or by income or by demographics, other things. So again, the key point is that these individual values aren't necessary to do this work. What's necessary is to be able to work on the data in various ways. But as long as you can work on the data, having individual values actually is not particularly helpful. And of course, it's a privacy problem. And as someone who's done quite a bit of data work, I can tell you that one actually very rarely looks at data values individually once you get past a given size, because it's simply not practical. You have hundreds of thousands of data points, and one data point doesn't help you very much. And if you do have, and the only times you really do look at them is when there's giant outliers or something, and you're why is there one person who's who appears to have visited 50 million websites, and that person's obviously probably not that person. So there are a variety of different measurement types that you like to collect. There's sort of simple statistical metrics, aggregates, like mean, median, sum, histograms, those kinds of things. The typical things you learn in a stats 101 class. And then there's things like relationships in multiple values. These are all stats 101 kind of things. Correlation coefficient, ordinary least squares, blah blah. this can go. This of course can get very complicated. Up to like machine learning algorithms. Nothing we're talking about today really will let you do will let you do a deep learning. Unfortunately. And then there's this very specific task, but actually quite a common task, which is common strings, which is often called heavy hitters. And the problem here is to say like what strings are like most common between people, and so like that can be a lot of different things. But a common example that Google gave in their report paper is what home pages are most common on people's machines. And so you don't want to know like what homepage someone has that like the only person has it, but if like half the population has it, you'd like to know that. And the nice thing about all these values, I say, is like just to pull back is that once again, they don't actually depend on knowing individual values; they only depend on knowing this aggregate. And this heavy hitters problem obviously has a property in that you only want the most common ones. You don't want the individuals. And that helps, by the way, mitigate the privacy of these heavy hitters, because if someone has as their homepage, they have their own some Google Doc that they accidentally set as like happens some Google Doc which is like sensitive. Well, you don't want to know necessarily. So so one example use case is user interests. So what kind of sites are users visiting? And again, I don't need to know, and typically no one needs to know exactly what sites it is. But you like say, okay, bucket sites by topic. So how many people are on medical sites? So you bucket sites by topic, and you count the number of like visits and minutes people spend on each topic. But again, even if you're not measuring individual sites, the topics themselves can be sensitive. So if someone is visiting a website associated with a particular medical condition, you might worry that they or someone in the family has that condition, and you don't want to collect that information. So it's like one problem statement is collect the distribution of time spent on each type of site. It's obvious to like be able to generalize this kind of problem. And anytime you have categorical information from users and you'd like to collect this category. So it's not not just necessarily sites. It's lots of other things as well. And again, one thing you're going to hear throughout this presentation is that these sort of stylized problems often can be bootstrapped into like a lot of different kinds of measurement can fit these kind of stylized problems. Another use case, which is which we see very often, is this like web compatibility problem. So the web is really big, and that websites sometimes will not work on a given browser, and so we see this very often that a website works fine like on Chrome, doesn't work on Firefox, or works fine on Firefox release, but doesn't work on Firefox beta. And users will sometimes report these problems, but often they do not. And developers sometimes report these problems, but often they do not. And so even when we have fairly gross interop problems, often they don't get reported. And even if they do get reported, the latency of the system means that like suddenly a lot of people experience problems before you've had any chance to fix it. This is like a really quite large problem for browsers like Safari and Firefox, where sometimes the developers not test on the product. So the good news is that often you can detect breakage on the client directly, either directly by the API fails, or they try to use the API which doesn't exist, or because the users like what they call like rage clicking, trying to reload the page over and over and over again in order to see hopefully it will fix, which sometimes it does, by the way. So a very specific case of this is that it wasn't quite web compatibility, but it's a similar kind of problem, which is many websites do this thing called fingerprinting, where they measure persistent properties to create a browser fingerprint. So this is an obvious threat to privacy. It's an alternative to using cookies, and we see it being used sometimes when cookies are unavailable or when the people don't trust cookies for some reason or other. This also is often detectable on the client. Because you can see use of APIs, it doesn't make any sense. So an example would be like they do WebRTC APIs, but then they don't actually establish a peer connection. So you're like, why are you collecting like the IP address, but you're not collecting a peer connection? So it's very hard to learn about these issues on a mass scale. And even though modern browsers have what's called telemetry, which is to say they report data back to the manufacturer, they do it only with basically non-sensitive data, because for obvious reasons, we wish to preserve the user's privacy and we don't wish to learn which website they're actually on. So there's a problem statement here, which is to like collect the sites where the client sees issues, but do it in a way where, actually I've written this problem statement wrong even. The problem statement here is collect the sites on which clients are aggregate seeing issues. I don't care what the site you're actually seeing issues on for the reasons indicated previously. So so pulling back, there are multiple kinds of privacy problems. So one privacy problem is collecting sensitive data which is directly tied to identifying information. So for instance, a concrete example, if I just report back if you have a program which report back what website everybody's going to, even if it's not tied, even if there's no like email address in there, the IP address is enough to see that, right? And so so like there's the first order privacy problem, which is just gathering like sensitive data with like a user identifier directly attached to it in some way. So that's problem one. Problem two is even if you don't have an identifier, collecting sensitive data along with some non-sensitive appearing identifying information. So as an example, Latanya Sweeney in 2014 pointed out that if I just had your zip code, your gender, and your date of birth, that's enough to identify like 87% of people in the United States. So it's a good example here is say like, look, is people's income individually isn't problematic, and like their birthday and zip code initials don't seem problematic. When you glue them all together, now I actually have like everybody's birthday, or not everybody's, but a lot of people's income individually. So we have to fix both these problems, or we're not going to be out of the woods. Okay, so the sort of natural thing everybody thinks to do at this point is say, well, what if we just collected the user information without any identifiers? So practically speaking, there's like the sort of dumb way to do this, which you say, well, we'll like strip the identifiers on our side, and you can just promise us that we don't do that. People do that, and like it's better than nothing. But technical controls are better than policy controls, and so the better thing to do is to strip the identifiers on the client side, which is the client side will strip out like on a web browser, strip out cookies and email addresses and stuff like that. And then you strip out, but that still leaves you with a lot of the networking metadata. You strip that out with a proxy. So you get some proxy, which is like not associated or at least not colluding with the collector, the data collector, and you end-to-end encrypt the report to the data collector, so the proxy can't see the data and the identifying information, and then the proxy strips off like the metadata, like the IP address. So the idea here is that the data is never concurrently identified and available. It's either encrypted or unidentifiable at the same time. So there's multiple technical ways to do this. There are like connection level proxies, like IPsec, 2017 Connect, Mask, and there's application proxies like OHI. So this is a great technology, and a technology which is very valuable in a number of cases. Unfortunately, it is imperfect. So good use cases here are when you have like semi-sensitive data, and you want to boost the privacy. So as I sort of mentioned, browsers do telemetry now, but they just throw away the IP address, hopefully at the other end, but which we try to do, but you don't know that it's happening. Also, individualized values where you don't like need to dig into the data. I'll get into this in a minute. And freeform data like JSON blobs, which is like hard to like do a lot of crypto on, like complicated crypto on. Also, for anything, by the way, which needs an answer, because the multi-party computation stuff I'm going to talk about in a minute does not work properly if you need an answer. It's one way only. So like DNS requests and safe browsing queries and stuff like that do well with proxies. And do I have like bad case? Yeah, good. I have bad use cases. Fantastic. So there's a number of cases where this is really useful. Unfortunately, there's cases where it falls down too. So one place where it falls down is if you have like what's called high dimensionality data. Say I have data where I have a lot of variables that I want to like look at their relationship with them. Going back to my income height example, for instance. Also the case when you want to look at subgroups. So you say like, look, I want to look at only people with this nationality, or if I want to do correlation or regression, any kind of stats processing. And the reason for this is that, as I was saying earlier, the more you glue together these like individually low sensitivity but high dimensionality data sets, the more you can identify people. And so there's this the example I gave of you know, birthday, zip code, and whatever, where it's perfectly natural to want to ask what's the correlation between zip code and income. But if I give you zip code, and it's perfectly natural to ask like what's the relationship between birthday and income. But if I like glue all those things together, suddenly I have identifying. And there's this famous other famous example of the Netflix data set where Narayanan demonstrated that you could like look at very small amounts of information at people's Netflix viewing histories and figure out how they were. So the problem is that if you're just going to like blanket anonymize, you need to break the data apart. You need to take each value and send it separately, unlinkably. But then when you do that, you can't do any of the stats analysis. It's also not very good for heavy hitters, because if you want to know only the top n values, then in order to actually figure out which one's the top n, you need to report them all. And so you say, look, you know, what I'd like to do is not see the, you know, Google Docs as I said at their homepage, but actually what happens is that they always send to the server and you stack rank them. So some technique for fixing that is really helpful. And so I think just not to foreshadow this too much, but like that's one of the things that Star does, that we're talking about later. It tries to like collect the data, but not see the ones that are on high dimensionality. And that's something that's in scope for GPU for PPM work as well. The good news is, like, this is a situation where cryptography can help us. There's been quite a bit of work on how to address this situation in the past 10 years. And we have cryptographic mechanisms for addressing this problem. So the basic technology, it's called MPC, multi-party computation. And the idea is you have two servers, and the servers are non-colluding. And what that means is that they interact with each other, but they're not working together to reveal your information. So the basic idea is that each client takes this data and it splits it up between two servers, and it sends like send to server A and send to server B. The servers basically take all the data from all the clients and they individually aggregate it. But the data is still encrypted, so they're doing it's a kind of homomorphic encryption, and they're computing an aggregate over the encrypted data. And then they take their aggregates, and they share them together, and when the shares can be reconstructed to produce the actual value. Just to think about where the situation is, the servers individually know who the clients are, but they don't get to see the client's individualized values, and the collector gets to see the aggregates, but never gets to see any individual value associated with anybody's data. So it's really important to the trust model here is, what the client's requirement is that the two servers don't collude. If the servers collude, they can compute individual values, and it's like totally over. The servers, in order to guarantee this, that they don't accidentally collude, is enforce various invariants like minimum batch size and query limits. This is the hard privacy requirement from the client side. The collector's requirement is actually, the collectors don't care if the servers collude, but they care the servers execute the protocol correctly, and either server can distort the results. So just to recap that, for the client to be safe, both servers have to cheat. For the client to be unsafe, both servers have to cheat. For the collector to be unsafe, only one server has to cheat. But from the privacy perspective, that's okay, because if one server cheats, it can't actually break the privacy invariance. This is, by the way, difficult. Both of these properties are difficult to verify, especially collusion, which can happen through side channels. But point-in-time audits are sort of the state of the art. And again, we're talking at data where. Sorry, I lost my train of thought there. It's 5 a.m. for me. So anyway, this is not necessarily straightforward to verify, but generally the idea is you can keep piling on more servers, and at some point the clients ask, do I really believe all these people are going to cheat? So I'm going to like very, very briefly sketch some of the cryptography just to give you a flavor of it. The sort of main protocol here is something called PRIA. Sort of the first one of these is like really was viable, and this is useful for computing like simple numeric aggregates. So the basic idea here, and sorry about a little bit of math, but is each client has like some individual value x of I. So like say it's like my height or my income or something like that, and I want to get the aggregate over that. So this is like all like high school math, which is like very nice. Actually, it's like elementary school math. So I generate some random value r sub I in a finite field P, and I send server 1 basically my share minus r sub I modulo P. So again, that's like the elementary school math part of it. And I send server 2 r sub I. And you should be able to persuade yourself pretty easily that if I take x sub I minus r sub I and I add r sub I, then I get x sub I back. So this information theoretically fine. And each server adds up the shares. So server 1 takes up all the x sub i's minus r sub i's, and server 2 takes all the r sub i's, right? And so now if you take all those and you add them up, congratulations, addition is commutative. And so you just cross out basically all the r sub i's and the minus r sub i's, and you get basically the sum of x sub i's, right? So what we've done is we created a situation where neither server saw the data, but you had the aggregate anyway. There is, I say this is also elementary school math. The non-elementary school math part of this is what happens if the clients lie. So there's a zero knowledge proof indicating the clients didn't say that I'm a million meters tall. The good news is that even this like really kind of like dumb encoding or very limited system can compute an enormous number of things. So just to give you a flavor of this, arithmetic mean is like easy to compute. Once you have sum, you divide sum by cardinality. That's like obvious. You can compute product by working in log space instead of working in linear space. This, by the way, is like how slide rules work. If you remember slide rules, you compute geometric mean from product and arithmetic. It's just the same way as arithmetic mean. You can compute variance and standard deviation the same way. You can do Boolean or and min max, or even ordinary least squares. And it's just about finding the right encoding for the data. So that's like really nice because like you've got the same basic structure, and you just basically say, oh, and now I'm encoding the data in a new way, and I can compute new things. Right. So as I was saying, we have this problem of bogus data. There are two kinds of bogus data. One of which is plausible but false data. So I say, look, I'm really 175 centimeters tall, but I say I'm 180 centimeters tall. This is a problem. Any surveying technique has this problem. People lie, and if you're going to trust them, you're going to trust them. The solution to this, as with any surveying technique, is you live with somewhat noisy data and you hope that the lying is unbiased. By the way, height, it probably isn't. People probably say the taller than they are. And then there's the question of completely ridiculous data. So I say I'm a kilometer tall. Well, I'm not a kilometer tall. Nobody's a kilometer tall. Or worse, maybe they say I'm -1 kilometer tall, which is like, if you can't see the individual values, what do you know? So in a standard system, what you do is you take the data as it comes in and you look at the data and you say like, well, I'm not going to accept anybody who says they're kilometer tall. I'll just throw that data out. But obviously, Prio, you can't do this. Data is encrypted. So the solution to this, and this is the fancy part, is each submission comes with a zero knowledge proof of validity. So in advance, you say, I'm only going to accept people who say they're between 100 centimeters tall and 200 centimeters tall. And maybe there's someone who's more than 200 centimeters tall. I think there is. But we'll just say, look, we'll call them 200 centimeters and they'll be okay. And similarly below 100 centimeters. The zero knowledge proofs just prove that the encoding this is correctly encoded, which with math that I will not attempt to explain, though perhaps Chris Patton can. The servers work together to validate the proof because individually they shouldn't be able to, always real information of the data, and you only aggregate submissions with valid proofs. So there's basically this filtering stage that I haven't shown. So you can also collect, user interest with this technology. Every user gets a bucket, and every user interest gets a bucket. So if I have 100 user interests, 100 buckets, and the user reports the amount of time spent in each bucket, including zeros, by the way. So if I didn't spend any time on car websites, it still has to say 0. It still has to say I wasn't on a car site. And you just Pareto sum them up. So it's like really straightforward. You get histograms. It's beautiful, right? And the servers, again, only the aggregates, not the values for each category. This is all fine. As I sort of note in this footnote, if you also report time squared, you can get standard deviation because that's all you really need to compute standard deviation. So that's all sort of okay, except that that's all sort of okay, except that it doesn't scale well. So if there's 100 user interests, I have to report 100 integers. But if there's 1,000,000 user interests, I have to report 1,000,000 integers. And the intuition for this is that if there are integers for which I have no value at all, and I just report nothing, it's fine. You can certainly conclude there was no value, but now I wasn't interested, and you can assume that anything I did report a number on, I was interested in. So you have to report all the values. So it doesn't scale well at all. So there's this there's this new technology, even newer, called Poplar. And I don't know why I still have it called HITS here. I thought I replaced all those. But same people as Prio, that basically works by collecting strings. So instead of having, so you could do the same thing. You basically say each interest is mapped to a string. You can even do a URL, and each client reports the string that they're most interested in, or the top 5 strings they're most interested in, right? And then the servers can join, and the servers can jointly figure out which ones are most popular. This is really cool for like CS people. The way this works is that you can basically take the set of submissions, and because things are unknown, you got to figure out what things are most popular. And so you're able to ask this question: how many strings have prefix P, and how many strings have prefix P with a 0 on the end versus 1 on the end, right? And so now you have a binary tree, and you can just binary search on the tree and find the most popular things. So it's like a very clever intuition, and very powerful scheme. This lets you collect, the most popular URLs, for instance, or as I say, basically any open-ended string. So how would I imagine using this? Because that's like a real use case. Every time the site is broken, the client creates a report for each site which is broken, and then you use this technology to determine the top sites. And so then you go and you try to investigate them, right? And so the nice thing is the servers collectively only learn the most important sites. They don't learn who reported them, and they don't learn the low cardinality that you don't care about. Because as I said, this is arranged in a binary tree, and so you start and you say here are all the reports, and then on the left side of the tree are half of them. But at some point you get down and say there's only 50 reports to the left side of the tree, and you're still way at the top of the URL because most of the URLs you still haven't seen yet because you're only going down one byte at a time. Okay, so second piece of this puzzle is that sometimes you want to, as I said, dig into the data, right? So I just described a sort of one-way pre-program kind of measurement, but you can also have measurement where you want to get into the data later. So you say, look, I have a distribution of income, but I really want to look at at birthdays and kind of whatever, right? And so the way you do this is that you report the demographic data in the submission itself, and that basically gets carried along, but that's unencrypted, and that's because that's basically non-sensitive. You don't worry about it so much. And then the servers can say, okay, slice the data, only ask for the aggregates over. I only ask for the aggregates with a set of birthdays, with a set of zip codes, right? So this is a powerful technology. The challenge, some challenge in that if I allow you to make as many queries as you want, obviously you can slice it down to individual data values. And even if I say that you can only ask for sets of no smaller than 1,000, what I can do is I can create 2 sets, one with a given user and one without, and then I can pull out IS value. So there's a bunch of possible defenses here, which probably all have to be used together. Minimum batch size, anti-replay, so you can't ask this question of the same data multiple times or too many times. Randomization noise for differential privacy, those kinds of things. So I know those are all in scope for each of these proposals. As I said, that there's a main document here, and the one which is, I believe, in the charter specifically is this draft GPW PPM, which I guess I have the wrong version number here, which is a generic modular protocol for any of these MPC flavor schemes. Initially implements Prio and Poplar, which I really thought I did search and replace in these slides, but may have forgot to rerun them. Poplar is the new name for this thing we're calling HITS. And it's compatible basically, a pluggable system, so it's compatible with anything that can be fit in this MPC flavor. And to give you a concrete example of that, the proposal Facebook and Mozilla worked out for interoperable private attribution also fits reasonably well in this framework. So it's built on top of a web services infrastructure, so it's easy to implement with existing stuff, et cetera, the usual thing. And just very briefly, here's what the architecture looks like. Like I said before, you have these clients. Each client sends the shares, and then you have this back and forth aggregates computation, and it goes to the collector. And I'm not going to bother to really kind of go into this at all because I know Pat has plenty of material on it. And so now I have questions if anybody has any.
Hi everyone. We're running a little bit behind schedule. I'd love to get into the next presentations. Thanks Eric, for that really clear and educational introduction. If anybody has burning questions, feel free to jump into the queue now. But also let's start getting ready for our next presentation. Okay, Chris, we see your face. We don't see your slides.
Oh, I requested to share them.
Yes, I approved that. Okay, let's try this way.
Oh, I guess I can share them from this upload flow. Share. So I can't do from Google Docs, but we can do the cool.
They're shared.
Everyone can see that, right?
Working.
Cool, and I have full control. I am ready to go. Okay, yeah. Thank you, Ecker. That was a wonderful introduction to the crazy world we just dove into with PPM. Okay, so I'm going to start off. The next few talks are kind of describing some open issues that have come up over the last several months that we've been kicking around this draft that we're talking about. And so I have the pleasure of talking about one of these open questions, and it has to do with how clients upload their reports to the aggregators, the two servers that Ecker talked about. Okay, so I wanted to give a quick overview of how we think about the architecture of this system, and we really think of PPM as being three sub-protocols that are executed simultaneously. So the upload flow is clients push their reports. These are input. This is the input shares, the secret shares of their input to the leader, and these are encrypted under the public keys of each of the aggregators, so the leader doesn't end up seeing them in the clear. And then there's the aggregate flow, which is where the aggregators interact with one another in order to verify the validity of the inputs they're consuming, as well as aggregate them and compute shares of the aggregate results.
Eric, did you have a question?
Yeah, could I just cut in for 1 second? Chris,
Yeah,
I think
go
it'd be
ahead.
really helpful if you took 2 minutes and covered the material that I foolishly thought you were going to cover, which is basically just briefly describing how the architecture works in a slightly more general sense. You're only showing, I mean, I just want to make sure, like I know this material, but I just want to make sure you cover like exactly how people should think about the whole system as a whole. Do you think that'd be useful?
I mean, I think that's what this slide's about, but maybe you're looking for something else.
Maybe I am. I'm sorry. It's very early in the morning for me as well.
It's okay.
Yeah. Okay. Go ahead. I'm sorry. I didn't mean to interrupt you. I just want to make sure people are situated before you ask people to make decisions. I want to make sure people are situated.
Okay. Yeah. I mean, that's what I'm attempting to do here. So if anything's not clear at the end of the slide, people please get in the queue and ask questions, because we're gonna bring up the pros and cons of two different approaches here. Okay. So so the upload clients upload their reports to the leader. The report contains the input shares, and they're encrypted to the public keys of the leader and helper, and that's so that the leader doesn't ever see the input shares in the clear. In the aggregate flow, this is where the input validation that Ecker described happens, and aggregation of the input shares. And then finally, the collect flow is there's the data collector we think of as a different entity that interacts with the leader in order to get the final aggregate result. And so it's asking the leader for the aggregate shares. Okay. So does anybody have questions about the architecture? I guess this is the next question. I'll look at the chat real quick. Okay. I'm going to assume, okay, go ahead, Penguin.
I have a question. What if the leader and the helper and they conspire with each other? Is there a possibility?
Yeah, so I mean, what as Ecker pointed out, something that we're going to be assuming is that the leader and helper are not colluding, and we can discuss like I think for now I think we should take that as granted, but we can discuss like I think the working group might want to discuss ways of actually verifying or non-collusion. Ecker, go ahead.
Okay, thank you.
I have a leading question, which is how do the how do the leader and helper get coordinated so they're doing the same thing, and know which measurements are being collected and what anything individually means, and like those kinds of things, right?
Do you mean how they're configured? Okay. Yeah, I think that so I guess what's missing here is that what the PPM's protocol is meant to specify. So there's in the CFRG we're working on a document that describes the underlying crypto bits, like so Prio and Poplar and other instantiations of like a thing of the multi-party computation step. And so all of the parties have to be configured to execute the same what we call a verifiable distributed aggregation function, VDAF.
I was hoping to talk about tasks for 30 seconds.
Okay. Okay. So, okay. A task is, sorry, it's also early in the morning for me. When a collector, okay, so when a client is uploading reports, it needs to know where to send reports, how to generate them, and this is determined by what we call a PPM task. And the task is supposed to specify all of the things that all of the parties need to agree on in order to do the computation. I'm not sure what else there is to say about that.
Let's move on to the next question.
Mariana, you're in the queue.
Do you hear me?
Yes.
Okay, sorry, this resets all the time. So my question is related to, are you envisioning to allow any options of this architecture in the sense that maybe there are applications where the party collecting the data, the reports, is different from any of the aggregators? Right? There might be a reason that it's easy to have a party online that is different from the aggregators that is collecting all the reports. And an example of such a system is the deployment that we have in exposure notifications, where our collectors, our ingestion servers, are neither of the aggregators. And I can also imagine other applications where maybe you want to avoid the additional communication cost of the leader sending to the helper reports.
Yeah, so that's what that. Yeah, so sorry to interrupt. That's what this presentation is about, is an alternative architecture that's been proposed. And we're weighing, like, the goal is, in my talk, is to weigh the pros and cons of the two different approaches. And to your first question, yeah, I mean, I think that that's totally on the table, but it's something that also needs to be discussed. So the perspective I'm coming from is from the current draft, and which I think I guess we could have spent more time describing at a high level. But yeah, so that's totally on the table, but it would need to be in the draft.
Okay, thank you.
Any other questions? Okay, I unfortunately, oh, go ahead, Daniel.
Yeah. we, in the previous slide deck, we're talking about aggregators. And in this slide, we're not seeing there's a term aggregation, but
Yeah.
it doesn't mention who aggregators are. So maybe
Yeah,
that's the piece
so
that I'm missing.
I apologize for that. The leader and helper are both aggregators. So there's three different kinds of roles. There's the client, and the client, an aggregator, and the collector. The leader and helper are both two different types of aggregator, and the only difference is that the leader is kind of holding the state of the aggregation flow. I was hoping that would be clear on Ecker's slides, but I guess not. I apologize for that. I should have labeled this better.
That makes sense. So the blue squares are aggregators.
Yes.
Got it. Thanks.
Okay, I will go through this very quickly. I want to be sure to save time for everybody else. So this is what we have today, this leader upload flow, where clients send their both encrypted input shares to the leader. And an alternative flow, as Mariana suggested, is we could instead have the client send a share of its report to each of the aggregators. So each of these report shares would just have the encrypted input share for that aggregator. So I think that in some sense the split upload model is a little bit more natural, and as Mariana mentioned, this is what's already been deployed for an earlier iteration of Prio. So why did we do it this way? Why do we do it this way? So I think the main motivation was we wanted to make it as cheap as possible to stand up the helper aggregator. So with the current architecture, only the leader has to be able to handle a lot of bandwidth, and is exposed as a normal web service to client traffic. And the aggregation flow has less bandwidth because, first of all, it doesn't have to send both encrypted input shares to its peer. So we save a little bit in bandwidth. And also the leader can throttle traffic if it needs to, if the helper is falling behind, or if it's falling behind, it doesn't have to be totally online the way the leader has to in the upload flow. And then the collect flow is just there's this, the collector is just getting aggregate results, which is fairly cheap to do. Another motivation is that there's kind of a race condition in split mode where the leader's receiving report shares and can initiate the aggregation flow at any time. And then when the helper receives its report share. So if the helper receives its report share first, before the leader begins, if the helper doesn't receive the report share before the leader receives its report share and begins aggregation, then we might have to drop that report. And there's ways to fix this in the protocol. And then the third point is that in the split upload world, the upload flow is more likely to fail because the client is making two HTTP requests to two different servers rather than just one to one server. The big downside to the leader upload model, as Mariana suggested, is that the aggregation flow has higher than necessary bandwidth because basically we're sending, the client could have sent the report share instead of the leader. And this is a significant problem for Poplar because input shares are big, and we're going to run the aggregation flow several times on the same set of reports in order to finish the computation of heavy hitters. And so higher bandwidth between the leader and the helper means higher egress costs between cloud providers, which is an important consideration for us. So I think we have mainly two options. which is what I'd like to discuss. But I guess we should maybe just take it to the list because we're running low on time. We can stick with the leader upload model and try to mitigate its downside. That is, don't require retransmitting the report shares in the protocol. And there's a question of whether this is like enough to reduce the egress costs, or we can consider adopting the split upload flow and leave and I don't have much time to talk about this. There's options for it's possible that we can mitigate the downsides but kind of leaving it up to the deployment. So there's been this suggestion of putting an adjuster between the client and the leader and the helper, which can coordinate transmission of report shares and solve some of the coordination problems. Then there's this question that Ecker brought up on the list, which is, in what sense is the ingester trusted or untrusted? So that's my time. I'll kick it back to Ben.
Okay, thank you, Chris. I want to make sure that we get through all the presentations on this topic. We did build in time for questions after the 3 discussions on this draft. So if folks have really high priority brief questions, jump in, but also let's get set up for the next set of slides. Oops. Eric?
I just want to make sure, like I see in the budget discussion in the chat. Sorry, make sure people understand what's at stake here, which is primarily what's at stake here is whether or not the role of distributing the data to the the role the leader has to perform is orchestrating the computation, and the role that is incidentally performing is distributing the data to the helpers, right? And so at stake here is whether we should separate out those roles and have the role of distributing the data to the helpers be done separately from the and directly in this case from the role of orchestrating the computation. So that's what's at stake here. It's not a security question. It's really it's largely an operational question.
I think the other comment in the chat was that if it's possible to describe the system where the role of coordinating the computation does not require participating in the computation, that might also make it cleaner, right? You could say there's the coordinator, and the coordinator may also play a role as one of the participants in the computation. But I don't understand the actual mechanics of the computation well enough to know whether those roles can be split out. I think that's the I think that was Jonathan Lennox's recommendation.
I think that there is. I think that's an interesting suggestion. I think. I mean, you could I think you could imagine it would be. I think it would be nice to cleanly separate those things. I don't know if it's that easy, at least to specify. But yeah, I think it's there's a lot to discuss here, and I think. Hopefully we can have a good discussion about this on the list.
Just to answer that question a little bit. Just to answer that question a little bit. I think the challenge is that from the perspective of running the computation, it's actually quite straightforward to specify as if the leader we're not one of the aggregators, but in order to actually do the computation, because you're really just sending messages saying compute this, but in order to actually do the computation, you have to know which shares are available in order to describe them to each side so they can be aggregated. And so we have to invent some mechanism by which the leader learned which shares were available in order to do that computation. And that would be new protocol mechanics, or we have to just say it's magic. And so that I'm sort of loath to describe those new protocol mechanics if no one's actually going to implement it that way. But perhaps you could just say it was a magic channel.
Okay, let's move to Chris Wood.
All right. Good morning, everyone. This is going to follow on the heels of some of the comments and questions that came up during Chris's presentation, in particular, how the collect sort of piece of the protocol works, and what sort of requirements you need to have in place in order to ensure that the resulting PPM protocol has the desired privacy properties that you want, that Ecker kind of alluded to in his overview. It's going to get a bit technical in terms of, I guess, how the particular collect flow works for the current instantiation of PPM. So if you have any questions along the way, feel free to chime in or hop in the queue or whatever, and I'll try to answer them. So at the highest of levels, this is, you've seen this diagram in different shapes and forms before, but this is how the collect flow basically works. The collector that interacts with the leader for the purposes of like initiating a collection, which either in turn will trigger some aggregation to happen between the different aggregators, or aggregation will happen preemptively, depending on what type of VDAF is being used. Once aggregation is done, leader will produce basically an aggregate share, or each aggregator will produce an aggregate share, and then the collector will eventually query the leader for these aggregate shares, and then combine them together to get the aggregate result. Each aggregator also maintains during the aggregation, I guess, flow of this in this particular interaction, all of the individual reports that were submitted by clients, the individual reports themselves, as well as also sort of the aggregates that are accumulated as the aggregation happens, such that it can present them to the collector. And the requirements here are, how do in what ways can the collector ask the aggregators for different aggregate outputs, such that the privacy requirement is satisfied. And by the privacy requirement, what we mean basically is that the aggregation output ensures that there's some minimum number of reports that went into it, where a minimum number of reports is something that's configured as part of a measurement task in the system. So all of the entities that are participating for a particular measurement agree on what this min batch size is, this minimum threshold is. And the requirement is that no matter how the collector chooses to query and interact with the aggregators, it cannot produce or derive in any way an aggregate that was based on fewer reports than this threshold. There's also, of course, a correctness requirement, which is that aggregation that is either triggered by collection or happens before collection, actually, the collect request actually comes in, includes basically the same reports. So if a client, if there's n reports from n different clients, or n shares of n reports from n different clients, those are all included in the same aggregate. And we don't have like one aggregator aggregating some set of report shares and another aggregator aggregating a different set of report shares, because the output would be garbage. So these are kind of the two informal goals of collection, and try to walk through why currently PPM does not satisfy the latter goal, and ask some questions that hopefully get us towards thinking about how it might satisfy this later down the road. So during aggregation, aggregators kind of keep track of individual report shares in batches, and batches are divided over time, where the length of time is some parameter we call min batch duration. So it might be a day, might be a week or an hour, whatever. A report is tagged with a particular time stamp, effectively, and that puts it in one of these time windows. And collect requests, when they are issued by the collector, indicate the time window over which the collector wants collection to occur. Currently, the collect request, the parameters of the collect request, in particular the time parameters, must align with batch window boundaries. So they must align like on the picture here on like t-1 or t or t+1 or whatever, that's effectively kind of the only constraint. The current validation for a collect request is basically it's composed of two steps. The first of which is to check to see that the time parameters do indeed align on these batch window boundaries, and the second of which is to make sure that for the given boundary or for the given time window specified by a single collect request, independent of any previous collect requests, the number of reports that are covered in that particular time window exceeds the minimum threshold size, this min batch size. So as an example, imagine you had a collect request for the window of t-1 to t. If you were to look at the two criteria here, it's indeed a valid window because it aligns on the boundaries, and totally arbitrary, but like I've tried to draw the picture such that it's like, yes, this is indeed a valid size. There's enough reports. There's not too many reports that go in this particular window. So both criteria are met, and this collect request would be satisfied. Similarly, you could ask for this collect request. Again, time window is valid because it aligns on the batch window boundaries. And the size is also valid because it covers simply more reports than the previous collect request. Martin, I just noticed you're in the queue. I don't know when you joined the queue, but is it a clarifying question?
Yeah. So how does the collector know how many events are in this window when it goes to make the query?
How does the collector know?
So if the collector is going to ask for, say, t+1 and t+2, which have what appears to be a total of one sample submitted, that's not going to meet your minimum bounds.
That's right.
So how does it know not to do that?
It doesn't.
Wonderful. Okay, thanks.
Right. I mean, the collector doesn't know how many things go in the report until it asks, or how many things are in aggregate until it asks, I guess. And it gets an output from the system indicating that there were indeed enough things in that particular window, or no, there were not enough things in the window, so an aggregate could not be produced. But anyways, if you look at these two collect requests independently, they seem valid. They check both criteria. Unfortunately, however, it's pretty trivial if you sort of only validate that these collect requests are valid in isolation. It's trivial for a malicious collector to basically use the output to compute an aggregate that is composed of less than the threshold. If you think of these as just like the collect request yielding like a set of reports, then you can just like compute the set difference between the first collect request, or the output from the first collect request, and the output from the second collect request. And in this particular example, that set difference would yield exactly one record or one report, which is unique to some client, breaking the informal privacy goal that we had at the beginning. So this is clearly a problem and something we need to fix. So it's kind of an open issue in the draft right now. Another thing to consider in the collect request flow and the collect flow in general is that people may want to collect or issue queries for parameters that are not only constrained in time, but also, let's say, in space. So for example, you might want to say, give me the aggregate for this particular time window that came from all clients that have the specific user agent string. Or you might want to say, give me all the aggregates in this time window for reports that came from this particular geographic region, to allow you to sort of drill down into errors. If, like, for example, these are like 100 reports, then you might want to say, give me all the aggregates for this particular time window that came from all clients that have the specific user agent string. Or you might want to say, give me all the aggregates in this time window for reports that came from this particular geographic region, to allow you to sort of drill down into errors. If, like, for example, these are like measurements you're collecting from the perspective of web browser. And currently, the collect request is only parameterized in time and has no notion of space. And indeed, like the protocol itself is completely unaware of this like additional like metadata, so to speak. So given these two things, the desire to sort of maintain this this informal privacy goal stated above or previously, as well as the potential flexibility you might want in time and space. I think the real privacy goal can kind of be stated as such at the top, and that is like any sequence of collect requests with any time and space constraint parameters. Given any particular sequence, the collector must not be able to produce, deduce, compute, whatever, an aggregate that is composed of less than the threshold number of report shares. It would be fairly easy to sort of enforce this rule if the protocol was aware of this sort of space dimension. How that's actually done mechanically, like how reports are tagged in space like they are in time, is sort of an open question. Do we want to even do that as an open question? But I think we understand fairly well how we would implement this. It's just a question of how these different constraints and parameters are expressed in the collect request. Sam, do you have a question?
Sorry, not as chair. Tell me about how you deal with Sybil attacks here. How do you keep the collector itself from being its own Sybil contributor?
Sybil attacks are a different issue entirely, I think, and I'm not trying to address them in this particular discussion. We do have to have like accommodations for Sybil attacks, like either clients themselves introducing random reports or leaders themselves introducing random reports. But that's separate from how the collector queries for things and tries to produce or tries to violate the privacy requirements.
I'm not convinced as to it being separate, but I'll wait to hear this later.
Okay. So the questions I have for the group, basically, first, is the validation problem clear? In particular, like the current issue in the draft that I sort of described it, is it clear and understandable to folks? Is the sort of informal privacy requirement also clear? And if so, how do we want to sort of augment the protocol, if at all, to accommodate queries or allow people to query on the basis of time as well as potentially on the basis of space? Or like you might imagine just simply relying on the fact that the aggregation protocol itself will always yield, or the output of the aggregation protocol will always ensure that both aggregators agree on the same reports that went into a particular aggregate. So you may not need to specify in full detail, for example, how collection requests are exactly how the validation criteria is to be enforced. You might just rely on the fact that the aggregate protocol sort of enforces that for you. And there's probably other questions as well. Stephen?
Hi, Stephen Farrell. So Chris, you talked about time and space in Privacy Pass yesterday, and those are a different space.
Sorry, I just heard Privacy Pass. It was very quiet.
Sorry. So yesterday in Privacy Pass, the phrase, the concept of time and space was used, but in a different way, right?
Yeah.
I wasn't sure I liked it then, but I definitely don't like it here, I think, because what you're saying about space here is really anything you can query on or something, is it? It's not a single dimension.
I tend to think of it as like just a bit string. The bit string might be like, you might encode like the user agent in the bit string, might encode like geographic data in the bit string, but I guess it depends on your definition of what space is. I think going back to the examples is probably the easiest way to think of space. So like you might imagine like the space constraints being a fixed set of user agents. And each report being associated with a particular user agent or something.
Yeah. Okay. So I guess I'd like to understand that better, because being able to query on the UA string implies that the UA string is visible to all these entities, right?
That's right. I think that's a necessary requirement if you want to enforce the privacy requirement on the basis. If you want to allow people to query based on these additional parameters, then I think those parameters need to be visible to the people who enforce the validation criteria.
Right. Okay. So I think I'd like to understand how we define space. In other words, what we make visible to all these entities.
Yeah,
Not
I
right
think
now,
that's
but, over the development of the protocol. I'm not asking we to understand it right now.
Yeah, I think that's a good point. And I think this goes to how much sort of flexibility, query flexibility you want in the collect flow. Whether or not you want to allow like any of this additional data to be expressed and as a result be sort of exposed to the aggregators or not. The utility of the collection sort of depends on what information is available and what's not.
Thanks. In the interest of time, I think we should move to Tim's presentation now.
Thank you. Okay, I'm going to tempt fate and try to share PDF here. Ooh. All right, cool, that works. Okay, all right, let's get into it. So bear with me, a number of these, I think a lot of our material today was written under the assumption that the folks have a lot of familiarity with the draft. So yeah, bear with me if a lot of this gets too technical or too into detail about the state of draft 01. Okay, so we're going to talk now about the current author's draft of the specification that we've been working on, as well as some work that a few of us have been doing that goes beyond that draft. Cool. All right, so in anticipation of this week's meeting, we submitted a new author's draft of the PPM specification, which is draft 01. Which contains quite a lot of changes relative to draft 00 that was submitted back at IETF 112 for the BOF. We're going to cover a number of those changes as we work through this deck. But first, let's talk about the status of this current draft. So to briskly recap, this draft specifies PPM, which is a protocol framework for privately computing aggregate functions. It's based on PRIO, but we've generalized from there so that it can work with any instantiation of a verifiable distributed aggregation function, which is a specification that's being discussed in the CFRG. PPM is designed to coordinate the execution of VDAFs across multiple non-colluding aggregators. And the sharing of inputs across both servers is how PPM deployments provide meaningful privacy to users. So as Ecker explained to us earlier, this targets a variety of motivating use cases ranging from simple statistics to the heavy hitters problem. All right, we also covered earlier very briskly how PPM is composed of 3 different sub-protocols that execute simultaneously. The upload flow is for clients to secret share their inputs and upload them to aggregators. The aggregation flow is where the leader and helper interact to verify the validity of inputs and then aggregate the reports and compute aggregate shares. And finally, the collect flow, which Chris Wood just gave us some insight into, is how the collector gets aggregate shares from the leader to get final results. So we know from some experience that draft 01 is almost fully implementable, at least like the happy path of uploading reports and computing aggregates is implementable. And we feel it satisfies the key deliverables defined in the PPM working group's charters. So in particular, we have mechanisms for client submission of measurements, for the joint evaluation of proofs of validity of those measurements, and for the computation of aggregates to be delivered to some end recipient. And all of these are defined in a way that makes them flexible enough to accommodate multiple underlying algorithms through the VDAF abstraction. So we're going to discuss later, I think, adoption of this draft, but I suppose I want to say at this stage that we think that this draft is good enough to be adopted by the working group. Okay, more on that later, I suppose. Moving on. So going past draft 01, we at ISRG and our colleagues at the Cloudflare research team, we've been working on a set of proposed changes that we're calling them interoperability target. So our teams have been independently implementing the specification, and our objective is to get our aggregator implementations to talk to each other in an experimental setup. So we've been taking the things that we learn while we write code, and we're integrating them into a set of specification changes that we're calling an interop target, which is a set which, excuse me, which is meant to be an iteration on draft 01 that we think can actually be implemented. So our goals here are to run a deployment of PPM using the Prio 3 based VDAFs, since the Poplar 1 VDAF isn't quite ready yet. So this ought to let us hammer out a bunch of interesting protocol edge cases and some important error handling scenarios. And we're hoping to learn a lot about which parts of the specification are difficult either to implement or operationally. And what we'll learn can then be fed back into discussions in the working group and has proposed changes to the specification. Okay, so let's look at where we're at today with development. So the most substantial piece of progress that we can report is that the specification of the Prio 3 VDAFs has matured quite a bit. So you can take a look at that in draft 01 of the VDAF document, which was presented to CFRG, I believe, yesterday by Chris Patton and his co-authors. So we also have a complete implementation of that draft of Prio 3 VDAFs, along with test vectors for them in libprio RS, which is going to be used in both the Cloudflare and ISRG PPM implementations, and hopefully others in the future. So of course, you can find those documents and the implementation up on GitHub or on the data tracker at these links. So we at ISRG also currently have a toy implementation of PPM somewhere around draft 01. It's missing a number of important protocol features, and it's really just a toy that couldn't actually be deployed onto the internet. It can only talk to itself, not to any other implementations, and it has no persistent story. But it does demonstrate that the happy path of the protocol can be implemented end to end. That also is up on GitHub if you're interested. And finally, both at Cloudflare and ISRG, we're working on actual deployable implementations of the evolving interop target. Ours is up on GitHub, and Cloudflare's should be open source and public in the near future. Okay, now let's turn to looking at like what changes are we proposing in the interop protocol so far. So let's talk about the aggregate phase. So as we discussed earlier, right, PPM is made up of 3 sub-protocols: upload, aggregate, and collect. The meat of the complexity lives in the aggregate flow, and it consists of the coordinated execution of a VDAF across the 2 aggregators. We also refer to this frequently as preparing inputs, and what that means is taking input shares and transforming them into output shares that can be summed into aggregates. So what that means depends on the particular VDAF. It could just mean evaluating the validity proof, or in some other VDAFs, there might be some more significant transformation. All right, so as spelled out currently in draft 01, the specification lacks sufficient detail to really be implemented. So one of the things that the interop target does is to be more detailed about how to detect and handle disagreements between the aggregators. We've also updated PPM to use the current verbs and message types that are defined in draft 01 of the VDAF specification. So above the VDAF level, we also, relative to draft 01, have eliminated what was called the helper state blob. So back in draft 00, we had the goal of having no storage requirements for helpers. So the goal there was to foster a diversity of aggregator operators by making it as easy as possible for anyone to run a helper with minimal infrastructure requirements or operational overhead. But aggregating shares in a VDAF is inevitably a stateful process. That's because the coordinated evaluation of the proofs is a multi-round protocol, and there's a state that carries over from one round to the next. The VDAFs that we envision currently, so again, that's the different Prio 3 based ones and Poplar 1, are all 2-round protocols, but you could have arbitrarily many rounds of VDAFs that come along in the future. Excuse me, where was I? Okay, right. So our solution back in draft 00 and draft 01 was to shift the burden of storage onto the leader by having it hold on to the helper's encoded state across the sequence of aggregation protocol requests. So we see this illustrated in the sequence diagram over here on the right. In the first request, the leader is sending to the helper a sequence of encrypted report shares along with some other parameters needed for aggregation. Upon receipt, the helper decrypts his report shares and then runs the VDAF prepare start algorithm, which yields a sequence of prepare messages and some state related to preparation. So the helper would serialize its state and send it to the leader along with the first round prepare messages. The leader next combines the helper prepare message that it received with its own and sends the sequence of combined prepare messages for the helper. So that's one prepare message for each report, right? And sends to the helper also the serialized state blob that it received previously. So in this illustration, the second request from the leader happens to be sent to a different instance of the helper than the first time around. You might imagine that there are multiple replicas behind a load balancer. It looks like this is fine since all the state is in the serialized state blob. But of course, there were several downsides to this design. So the first is you're going to spend extra bandwidth transmitting the state back and forth over multiple rounds of the protocol. Further, its contents are secret, which means that the helper implementation has to be responsible for encrypting its serialized state to protect it from the leader tampering with it or just seeing it. And of course, we have to stop the leader from replaying old states into the helper. So anti-replay means the helper has to store a counter or something like that to prevent state rollbacks. And so we've already failed to meet our goal of no helper storage. Finally, this scheme makes it pretty hard to parallelize aggregation, which otherwise ought to be easy to do since the preparation of one share should be totally independent from the other, except for at some point updating an accumulator. So to see why parallelization is hard, we're going to look at another important change that happened between draft 00 and draft 01, which has to do with the protecting against the replay of reports, which is not to be confused with replaying state blobs. So in a PPM, a report is uniquely identified by a nonce, and a nonce consists of a timestamp along with a random 64-bit integer. So we have to prevent the leader from replaying a client report into the helper to rule out attacks that would enable the leader to learn something about the client input. In draft 00, this was solved by defining a total ordering over report nonces and then requiring the leader to send nonces to the helper in ascending order. The helper would then defend against replays by keeping track of the highest nonce it had ever seen and refusing any reports older than that. So this doesn't work though if you have multiple helper instances that are working in parallel. In this illustration, the leader has carved up the work of aggregating the K reports that fall into some aggregation into 3 chunks. Each meets the requirement of ascending nonces, but to meet the anti-replay requirements, the helper instances have to share the highest nonce counter, which is sort of shown in this like ambiguous cloud of storage on the right. So if the helper 3 happens to do its work first and then commits K as the highest nonce, then helpers 1 and 2 have to reject all the reports they get, which is obviously bad. So in draft 01, we acknowledged that we had over-indexed on the goal of lightweight helpers. And we accepted that requiring that helpers have a trusted database or some kind of trusted storage isn't really all that bad, especially since, as we discussed, draft 00 required them to have some kind of storage anyway. So in draft 01, instead of the highest nonce ever seen, helpers are required to keep track of all the nonces they've ever seen, up to some reasonable data retention period, so that they can refuse to aggregate a report if they know they've already been included in an aggregation. Helpers also have to keep track of which batch intervals they've serviced a collect request for, so they can refuse reports, new reports that fall into those intervals to mitigate some of the attacks that were talked about earlier by Chris Wood. But draft 01 still has the helper state blob and the attendant anti-replay counters. Since we already accepted non-trivial helper storage requirements, we decided in the interrupt target to take the next step and do away with helper state altogether. So instead, we require helpers to store their own intermediate state. But to preserve the nice property that different rounds of the prepare protocol don't have to be serviced by the same helper, we introduced instead the concept of an aggregation job ID, which is assigned by the leader when it constructs aggregation requests and can be used later by helper to look up the state associated with the preparation of a set of shares. But unlike the old helper state, the job IDs aren't secret and they don't require any replay attack mitigations. Okay. I think in the interest of time, I'm gonna skip over this. And okay, jump ahead to the topic of gracefully recovering from input preparation failures. This is a problem that we learned quite a lot about while operating the exposure notifications private analytics system over the last couple of years. So first, let's recall some of the math about how aggregations over these secret shares work. So suppose we have n values where each is sharded into one share for an aggregator A and the other for aggregator B, such that they sum back up to the original value, modulo some prime number P. So we compute aggregates by having each aggregator sum their sequence of shares. Then the sum of those sums is congruent to the sum over the original inputs, and again, all under modulo P. Okay, but for some large n, for some large number of reports n, we expect that errors will occur, such that there will be cases where one aggregator happens to accept a different set of shares than the other. So if 10 shares out of 1,000,000 get rejected, we still would like to be able to aggregate over the other 999,990 shares, because that's still a lot of good data. But we have to make sure that both aggregators are using the same set of shares. So recall that for each share V sub IA, that is to say, like the report, the IF report, and the share of the IF report for aggregator A, and V sub IB is effectively a random value in the field defined by P. And A, the aggregate result, is also a value in that field. So let's suppose that aggregator B drops its share of the kth report. The resulting aggregate is not just off by some well-defined epsilon or error bars you can reason about. It's going to be complete random garbage. And worse, because that random garbage is still a valid field element, you can't detect this corruption except for by heuristic means. Like say, you're measuring something like how many times did a user click a button, and you get some like absurdly huge number. So in the scope of the interop target, what we are aiming to do is to have each aggregator include some data in aggregate shares that will allow us to detect this kind of problem and measure how bad it is. Specifically, the leader and helper will exchange counts of reports earned in aggregation, as well as a checksum of the included report nonces, which is computed by XORing the SHA-256 hashes of each report's nonce. So this hashing scheme is unlikely to be adequate for any real security purpose, but we chose this because it doesn't depend on a consistent hashing order across aggregators. And since this measure is intended to detect implementation or design flaws in an experimental setting rather than to provide real resilience against malicious clients or servers in production deployments, it's okay if its security properties aren't all that strong. All right, so that's the highlights, some of the highlights of what we've been batting around as we work towards an interoperability deployment. So to reiterate, our goal here is is to operate an experimental deployment and then come out of that with some learnings, some experience, and some data that will allow us to start some discussions in the working group to then propose some changes to the protocol, and that hopefully will let us answer. Oh, sorry, Benjamin.
No, finish your sentence.
Okay, yeah, I'm just wrapping up the last slide. So the interesting questions that we're hoping to be able to discuss going forward with what we learn are, so for which interactions and to what extent should the PPM protocol specify authentication for requests and messages? Or instead of doing that, maybe we should be specifying transport security requirements and letting deployments choose for themselves how to meet them. Also, like there's some places where the protocol introduces shared secret parameters between actors, particularly between the aggregators. How are we going to go about negotiating those and in particularly rotating those? And then operationally, what is the life cycle of reports or for the state associated with their processing? When is it acceptable for one of the participating servers to discard old data? And to make that clear, might we need an explicit commit phase during the preparation protocol such that both aggregators can have high confidence that they're aggregating over the same set of shares? Okay, that's all I got. Thanks, everybody.
Thank you, Tim. In the interest of time, I don't think that we should attempt to discuss or answer these questions here. Obviously, these are important and deep questions, and we'll have to deal with them over the next weeks and months as a working group. I want to make sure that we have time for the DSS star presentation and broader discussion after that. So if there are very brief clarifying questions, feel free to get in the queue, but otherwise, let's bring up the DSS star presentation. I believe Alex Davidson is presenting.
Right. Cool. Cool. Can you hear me okay? Yeah. Yeah. Okay. Cool. Okay. Cool. Yeah. So I'm Alex. I'm going to be talking about Star, which is, as has been referenced previously, like an alternative protocol sort of idea that could potentially fit into the PPM framework. And yeah, so I'll just get straight into it. So Star is very similar to this like Poplar One approach that has been mentioned. So the idea is that we want to come up with a system that we can find like heavy hitting, like arbitrary data. Specifically, when we were building Star, we essentially want to provide k-anonymity for clients that provide sort of arbitrary data points. So the idea is that a number of clients would send data, and then when you've received K reports all containing the same data point, the aggregating server will be able to reveal them. So the reason that Star exists is you know, as we were designing the system, we were kind of looking at these heavy hitting protocols, and they were like, there was a number of issues that made it difficult for us to deploy them. So especially Poplar, if we just focus on that, as seeing as the functionality is quite similar, is that it's quite expensive to run. And also these like having to have this aggregation process between like multiple non-including servers was something that was quite difficult for us to get off the ground during the aggregation phase. So Star is kind of an attempt to build like a privacy preserving system that allows you to reveal these like heavy hitting data points without having to run aggregation collaboratively with these like non-colluding elements. And also, you know, along the way, obviously we want to preserve privacy, and then also like there was also like a goal of trying to use like simple cryptographic primitives and techniques where possible, rather than introducing like novel mechanisms for running this aggregation. So the idea behind Star hopefully is very simple. So it's split into 3 phases. So essentially the first phase is this randomness phase. And the idea behind that is this phase is that we're trying to establish a scenario where different clients non-interactively can establish secrets of the secret shares using any old like threshold secret sharing scheme of the same value that you'll be able to combine together. So this randomness phase essentially allows the clients to establish correlated randomness depending on their measurement data point. And later on in the measurement phase, the clients are going to sample sort of secret shares of that measurement. It's a little bit more complicated, and then send these measurements to the aggregation server. And then in the aggregation server, when the server receives like K of these shares, if K is the threshold in this secret sharing scheme, then they'll be able to reveal the measurement. So the randomness phase can be done in cooperation either with the randomness server or like alternatively locally, just derived from the measurement X, but that has like some security issues. And this is something that was already raised by previous protocol designs like Proclo by Google. One of the nice things about Star is you can include like additional auxiliary data as well with your measurements, but the threshold itself is only imposed on the measurement itself. And then I've written there's this notion of an epoch, which I will also talk about, which is defined by the randomness server. And the randomness server and the aggregation server here are non-colluding, but the idea is that they don't have to collaborate in the aggregation phase. Cool. So what exactly is happening here? So the idea is that if you sample, you can sample randomness locally using just like a hash function like defined over your measurement space. But that's going to only really work if you have high entropy measurement distributions, and it's not clear whether you know, such measurement distributions exist. And so one of the sort of things that we're introducing with Star is this like remote way of sampling randomness via an oblivious pseudorandom function, which is controlled by the randomness server. So clients submit their measurements obliviously, and the server evaluates the oblivious pseudorandom function over them using a secret key, which is kind of like tied to the epoch. So this like randomness that the client sample would then go into this like message construction algorithm. So the clients essentially encrypt their data point along with any auxiliary data, and then derive an encryption key from some portion of the randomness that they get. They secret share like this randomness that they use to derive the key, and this rand1 here is sort of like the correlated aspect where you can like construct shares like consistently without interacting as clients. And then they also introduce a tag, which
which is an important note for security. And essentially these tags would, when the clients then just send all these messages to the server somehow, and the server then groups together all the messages with common tags because these deterministically derived from the measurement, and then can recover the measurements themselves using this like secret sharing recovery process. Cool. So
Mariana is in the queue.
So I just have a clarifying question. The server here learns all the counts on tags in the clear.
Yes.
Right?
Yeah. That's
so
correct.
we are not protecting counts here.
We're not protecting counts. Yeah. So the server learns all the subsets of clients that share the same measurement, but doesn't necessarily learn the measurements themselves.
Okay.
Cool. So the security model that we use is obviously comparable with Poplar 1. So we need non-collusion of the randomness and aggregation servers to, for this to work for clients. We consider like a malicious adversary server that also may control a subset of clients to kind of like model this like Sybil attack propensity. And as Mariana just pointed out, the messages that encode the same measurements are leaked. So even if you don't reveal the measurement itself, the deterministic tag leaks which subsets like the messages belong to, and so you can see that. But the goals here are confidentiality, absolute confidentiality of the measurements that are sent by less than or equal to k clients, and like robustness of the aggregation. Cool. So I just want to talk a little bit about like the Sybil attack window for Star, because this is like the most damaging attack. So essentially we want because this deterministic tag is present in the messages, it allows the aggregation server potentially to try and learn the messages just by trying to like run like an offline dictionary attack on the measurement space. So obviously with the local model, this is absolutely possible. And so one of the reasons that we use this like remote model of sampling randomness is to kind of like shorten this attack window and also move the like offline dictionary attack to something online that has to be carried out with as queries to the randomness server. So yeah, like so in doing so, we kind of like ensure that as long as the client messages are sampled only in this window and then they're received afterwards, and the aggregation server's attack propensity is also limited to this window. Cool.
EKG in the queue.
Sorry, can you go back a slide? I just wanted to check if I'm understanding the. Sorry, one more slide. I'm still trying to wrap my head around this randomness server. I guess the previous slide looks like the client is sending X, the secret value, directly to the randomness server themselves. Mm-hmm. Is that right?
No, so the X is blinded. Well, it is in the sense that it's input to the OPRF, which by definition, like the client's input is blinded, so the random server never learns X.
Okay, all right. Sorry, I didn't understand how the OPRF is working in the network call on the previous slide. The ladder diagram makes it look like X is being sent directly.
Sorry, yeah, this diagram is not that helpful for explaining how the random server actually works. But
okay.
But yeah, so this OPRF is as defined in like the oblivious unit random functions draft as that's currently with the CFRG. So essentially the client's input is blinded beforehand, and then like the server evaluates the function on it, and the client receives the response and then can unblind it and then gets the like real value output.
Got it. Okay. Thank you. Sorry for the rollback.
No, not at all. Not at all. It's a problem with the slides, right? So cool. Where was that? Okay, yeah. So just as a quick comparison with Poplar 1, so in Star, clients can send arbitrary auxiliary information with their data point, which may or may not be useful. Star, as I mentioned, Star leakage reveals all the subsets of measurements that hide the same measurement, even if the threshold is not satisfied, which is obviously very important. One of the things that Poplar 1 does is, it may even be part of the functionality, is that it reveals all the heavy hitting prefixes of strings And for some of our use cases, we only wanted to reveal the heavy hitting string in its entirety rather than the prefix itself. One of the obviously star only during the aggregation phase only requires a single aggregation server, which makes things a lot more cost effective because you don't use any bandwidth and the computation itself is very minimal. In terms of how potentially star could fit into the PPM framework, or at least how we envision it, is that kind of this like leader and collector in this diagram. In star, these are kind of the same entity and there are just no helpers. So clients submit, you know, via some mechanism, either OHI or whatever, like an anonymizing proxy, or it doesn't even have to include an anonymizing proxy, but it massively improves privacy if you do, submits things to this entity and the entity just performs the aggregation and learns the output. So we you know, as I mentioned before, star is kind of like a trade-off between trying to reduce the cost while also trying to maintain some like meaningful privacy guarantees. And also not having like non-colluding entities work together to perform the aggregation. And so these are some of the things that we're trying to emphasize when we talk about the advantages of star. And also for functionality, we allow auxiliary data, which may or may not be useful, and simple cryptography in the sense that we don't have to implement quite complex new protocols in order to build the aggregation process. And so just to conclude, yeah, we think star provides kind of some, for at least for us, like provides like a privacy preserving reporting mechanism for, you know, entities with limited resources and without, you know, expert implementation knowledge. And we think that some of the trust assumptions are preferable to those made by you know, either Prio or Poplar. And so just to finish up, like some of the questions we wanted to ask is whether the working group is kind of interested in this as an alternative protocol spec. And if it was, would this star draft fit into like the working group and also the PPM kind of specification?
Thanks. Okay, I have two things I wanted to say. First, not as chair. So okay, let me step back one more step. We have 12 minutes by my clock before the end of the session. We have a lot of things that people want to talk about. I'll try to be fast. So first, not as chair. Do you think star can be expressed within the framework laid out by the Priv PPM draft as a VDAF? For example, could we represent the randomness server and OHI type proxy? Could we represent that as one helper and represent the aggregator as the other helper and lay out a VDAF protocol, even if it's not exactly natural?
I think currently the draft doesn't really allow for the star sort of, well, at least like the way that I've interpreted like the leader and the helpers. I don't think star necessarily fits into the like interaction process that's currently laid out. I think if there was some way of like building extra functionality into the OHI proxy, then maybe there'd be some way of like interacting with that in order to create some information and then like sending the reports through to the leader, which could also be a single entity in the case of star, perhaps. But yeah.
Okay. And secondly, as chair, I've heard several comments about draft adoption, especially for the Priv PPM draft. So I'd appreciate hearing from star authors and other people, if people could comment on whether they think the Priv PPM draft is ready for working group adoption. Thanks.
Alex, was so you mentioned that the differences in trust assumptions. Do you need the randomness server and the aggregation server to not collude?
Yeah. So you require both of those entities to not collude. Yeah.
Okay, so that's comparable, right?
It's comparable, but they don't have to, because they don't have to collaborate during the aggregation phase. You can kind of like, it's easier to split out the functionality. And one of one of the hopes with like OPRF based functionality is that we would have entities running OPRFs kind of as a service. And
Yeah.
at that point, it's easier from a practical perspective to argue that if you like an application server and an entity that just runs an OPRF kind of as a service are like non-colluding.
Right. Yeah, I most definitely, there's a huge advantages to not having to interact for aggregation. So I think that's a very attractive feature of Star.
I want to make a comment that I'm not sure I'm kind of buying that there are two different ways to view non-collusion. I feel like for me, if there is a non-collusion assumption, there is a non-collusion assumption in either protocol. So I would kind of challenge the statement that these are different first models.
Thanks, Mariana. It seems like something strange happened with the queue. A bunch of people were in the queue and then got out and back in.
I was in the queue, I thought, and then I don't seem to be, and now I am, and whatever.
I'm gonna, Eric, I saw you at the top of the queue before. If you want to briefly go ahead.
I want to clarify, make sure I understand your question, because if you asked whether we thought PPM the PRIV document was ready for acceptance, but then people were still talking about Star. So do you want to talk about both, or what? Just to be clear what the question was.
So, it sounds to me like, as chair, it sounds to me like the authors of the PRIV PPM draft largely feel that it's ready for adoption, although I haven't heard everybody comment on that. I wanted to also ask the Star draft authors what they thought of adopting the PRIV PPM draft, because and everybody else in the working group, because of course we adopt by rough consensus.
Since I am here, I will say that the PRIV PPM draft is ready for adoption. I think that I think that people were asking in the chat whether or not these were mutually exclusive. They're not. They're complementary. Each is good for some tasks. I don't think we have to. I think if we adopt PRIV PPM, we can certainly adopt Star later. And I think it's clear. It's certainly clear that they're not substitutes for each other entirely. So so I think like that they don't preclude each other at all.
DKG?
Sorry, I've lost my train of thought while trying to describe, so I will pass.
Martin?
I have to wait for the wonderful meet echo delay. So I sort of came into this thinking that the group would be adopting something. I think we'd be foolish not to do something that fits within our charter. I don't see any alternatives for the sort of things that are being achieved by the PRIO work, and I'd like to see a draft for that. I'm a little less clear on the sort of practical aspects of the Poplar stuff, but I'm happy to sort of take the PPM draft where it is right now. I'm not quite sure about the applicability of the Star stuff just yet. There's a bunch of sort of usage constraints that need to be better understood, I think. That's also true to some extent for the PRIO work as well. There are a number of questions that came up through the presentations, which I have to say left me less confident than more confident at the end of them, which is not usually how you want these things to go. But overall, I think we should be taking the something on at some point to a call for adoption on the list after this.
So I guess Becker had remarked that the Star and the PRIV or PRIO, I'm not sure what we're calling it, they're sort of compatible, and we could potentially do both. But I was looking at the charter, and the charter says that we will deliver one or more protocols which can accommodate multiple PPM algorithms. And so I wasn't really sure if if we did both Star and PRIO,
would those be different protocols, or would those be different algorithms within the same protocol? And I guess I'm directing that at Eckert, but really anyone who can answer.
Do you want me to jump in? I think they'd be different protocols. That was the question that was being asked earlier. I think about whether or not you could cram. I think that the term here. I think. So I mean, the primitive framework was designed to accommodate multiple, as Patton was saying, VDFs, which is the term, which is like the specific term he's using for algorithms. But I don't think it's really practical to cram star into as a VDIF. So I think that would be a different protocol. Which I mean, I suppose you might imagine that star had its own algorithm subsets, but I'm not aware of that. So I think it's they're two independent trees. I think.
All right, thanks.
I just wanted to respond quickly to something Martin had said, in particular around Poplar. I wanted to note the distinction between PPM, the framework that drives sort of the VDAF execution, and then the VDAF specification itself, which is happening in the CFRG, wherein Poplar and Prio-specific bits are being standardized. And the question here is whether or not PPM as a wrapper around VDAF is sort of an appropriate, good place to start. And all of the complexities that come with Poplar and whatnot, I think, or most of the complexities that come with Poplar can be relatively isolated and constrained within the context of the VDAF draft. That said, like, there are certain aspects of the VDAF execution that bubble up into PPM, like how the collector needs to drive collection, and there are multiple iterations of that. But in general, I wanted to make that split, like this is like protocol engineering work, and the CFRG VDAF stuff is more the crypto specific bits.
So I remember what my question was. Sorry, this is a question about star. It was unclear to me what the specific collusion risk is between the randomness server and the aggregator in star, and I wondered if the star, anybody from the star team, or Alex particularly, if you want to just try to summarize what you think the collusion risk is there.
Yeah, sure. So essentially, if the randomness server and the aggregation server colludes, then the randomness server can reveal the OPRF secret key to the aggregation server, and it kind of moves the online attack back to being like a local offline dictionary attack again against the measurement space. So it kind of reverts to kind of like the local model of sampling randomness. Does that make sense?
Yep, thanks.
David Skenazy, Google. I have to admit, I feel a bit more confused now than I did 2 hours ago, but
You're very quiet.
Okay, let me eat the mic. I have to admit that I feel more confused now than I was 2 hours ago, but I'm going to attribute that to it being Friday and I haven't slept enough this week. But I just wanted to say that this is a great starting point for the working group, and so I fully support adopting the PPM document.
Okay, Mariana, we tried to close the queue, but what I'll ask is everybody who's read the draft, could you please comment in Jabber whether you've read the PPM draft, so we have some idea of how many people have read the draft, and maybe while that's going on, Mariana can chime in.
I guess I just wanted to make the point that we actually implemented both Prio and Poplar. And in the question of whether they are really fitting together in a single framework, I would say yes. I think there are like trade-offs between communication and computation, but the main challenges that we kind of seen across all of the previous presentations are common across this protocol. So I would strongly say that they do fit in the same framework.
Okay, thanks to everybody for telling us that that you've reviewed the draft. It's great to see that there's been so much review. Unfortunately, we don't have time to run a live poll. I think it's too late for a hum. We are officially out of time, but we will, I think, run a call for adoption on the mailing list. I want to make sure to thank DKG for volunteering ahead of time to take notes. That was incredibly helpful. It saved us a bunch of time and made time for all of this great conversation. Roman
So-
is our AD. Roman.
I just wanted to jump in the end because I should have done in the beginning. I just wanted to thank you, Ben and Sam, for stepping up to serve as chairs and to convey how exciting it is to have a working group. And I also wanted to thank, as I did in SAG, the proponents of the working group for really helping us get from what often doesn't happen from a BOF to a working group by the next meeting. And that all comes through hard work and preparation. So again, to all those that were involved in that, much appreciated for making it easy to do good work in the community.
Yes, thanks again to Joe for being on site and making sure everything ran smoothly today. Okay, I think that this session is over. IETF 113 is over. Thanks everybody for coming. See you on the list.